Hello everybody, in this video I will show you how to use the Thevenin theorems to simplify a circuit and obtaining the Thevenin equivalent circuit for a given problem. So the Thevenin theorem simplifies a complex electrical network into a single voltage source and series resistor, representing the original circuit's behavior when connected to external components. So basically this sentence is telling us that we can simplify, for example, something like this. Okay, this thing here, actually this thing here, okay, all this thing inside here, all this circuit, okay, we can simplify this with something like this. I mean, this thing here is the same than this other thing on the left. And here we will have a voltage source we usually call VTH, standing for Thevenin voltage, and a series resistor which usually we call RTH, Thevenin resistance. Anyway, the names are totally arbitrary. So let's see this concept applied to some specific example. Let's do this first for a very simple circuit like this one. So we have this circuit, we have voltage source of 10 volt, two resistors. This is a simple voltage divider. So we have, imagine we want to calculate the equivalent Thevenin circuit between A and B with this. So what we do, first of all, is to calculate the voltage between A and B. In this case, this is a simple voltage divider. So we have that the voltage drop on R1 and the voltage drop on R2 are the same, and they are the half of this voltage. If you don't believe me, just do the mesh analysis, you will find out that it's true. So we have basically between A and B, we have 5 volts. So this one will be our Thevenin voltage. So if we have an equivalent circuit like this will be 5 volts. And the resistor here will be what we see from the A point to B point. So the resistor that we see from A to B, we see here, then split into two, and come back here, then here. We find here the voltage source V1. So we substitute this for a short circuit, okay, in the calculation of our equivalent Thevenin resistance, and we use this like this. So basically what we see from A to B, the resistance that you see between A and B is this thing here. Something like this, then a short circuit instead of a voltage source. So basically this is the parallel between R1 and R2. So in this case would be 1 kilo. So this simple case, we have this Thevenin equivalent circuit. What does it mean? That this thing here on the right behave exactly as the circuit on the left. We have here 5 volt if we connect no other resistors on this side, and if we connect a multimeter between point A and B of this circuit, and we want to measure the ohms between A and B, we will find out that we measure 1 kilo. And with our multimeter we measure the voltage between A and B, we will find out that it is 5 volt, which is clear from this drawing, and here we just simplify this. Okay, now let's go to something more complex. Well, actually the example that I will show you now is very simple. It's not so much complex than this, but I think that this can be helpful to understand some basic concept. So let's consider this circuit, for example, which is a little bit different from the previous one, in which we have just added one resistor here. And so we want to calculate again Thevenin voltage between point A and point B with this polarity. So we look at this mesh and we see that there is no current flowing in this R3 resistor as it is open, okay? And so the voltage here between A and B is equal to this voltage here between these 2 points, which is again half of 10 volt because of the voltage divider. So we can say that our Thevenin is again 5 volt. Okay, Thevenin is our 5 volt. Let's look now for our Thevenin. So in this case, if we repeat the analysis as in the previous case, we will see that now we see R3, then R2 here, R3, R2, and on this side R1. We substitute the voltage source with the short circuit. So now our RTH is equal to R3 plus the parallel between R1 and R2. Okay, so now is 1 kilo plus 1 kilo is 2 kilo. Okay, this is actually very simple, but I wanted to show you. So also you see this thing of the voltage here, which is the same as the voltage here. If you have any question, please comment this video and we'll try to explain you to solve your doubts. Okay, let's see another example, a little bit more complex to apply, in which we apply Thevenin equivalent circuit. So let's see a little bit more complex circuit like this one, which is actually one of the two that I showed at the beginning. So let's keep things simple and say that all resistors are equal to 1 ohm, that my voltage source VA, let's say VA for not confusing with volt, is equal to 5 volt, and my current source IA is equal to 1 milliampere. So, and I want to calculate the equivalent circuit in this point, between these 2 points, A and B, I'll say plus minus, with this polarity, the voltage, turning voltage, the point A and B. So, I have to know what is the voltage drop here, given the contribution of VA and IA. So I start with VA and I use the superposition effect, superposition theorem that I explained, that I showed you in a previous video. So let's go to it. Let's see the contribution of VA. VA, yeah. So I have to take substitute the current source with an open circuit and see how much is the voltage drop between A and B. Okay, so let's see this. We draw again the circuit, and we have the voltage source, resistor, open circuit. Then on this side, resistor, cable, resistor, open circuit. Okay, so the contribution of VA is actually very simple. We don't have any current flow in these branches. So basically, if this voltage, but this battery is 5 volt, we will have a difference of 5 volt also between all this point and this point. This means that, let's see this, plus here, minus here, we have 5 volt, so we have also 5 volt between these 2 points, and also 5 volt with these 2 points. We are just interested in this voltage drop. So we say that the contribution of VA to the voltage drop between A and B is 5 volt. Okay, so we write down this thing here. Let's say VAB 1, okay, is equal to 5 volt. Okay, let's delete this drawing and see the next one. the contribution of IA. For IA, I have to change my VA with a short circuit. So I put a short circuit instead of VA, and I put my resistor here, 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 then my voltage source, and then R, point B, and R. Okay, so I have 1 milliampere going into this mesh. Okay, so I actually can calculate all the voltage drop. All the resistors are 1 kilo. So, for example, in this resistor here, 1 kilo with 1 milliampere, I will have a voltage drop of 1 volt. The same thing here, 1 volt. Current flow in this direction, plus, minus 1 volt. No current flowing here, current go this way, 1 milliampere current plus minus 1 volt. If you're asking yourself why this plus minus with the current in this direction, let's watch another video that I put on my channel on this playlist. The name is Ohm's Law, something like this. Okay, so and convention and signs. So my question was, what is the voltage difference between this point and this point? Well, here I have no current flowing, so I have equipotential behavior. I mean, the voltage here will be equal to the voltage here because there is no current flowing in this resistor, so there is no voltage drop here. Basically, I can see that between this point and this point, I have 2 volt, 1 volt and 1 volt with this polarity minus plus, so an increase of voltage here, an increase of voltage here. So basically between these 2 points I have 2 volt between this point and this point. Okay, because from here to here I have 2 volt difference. Okay, so now the contribution with the voltage, the current source IA to the voltage drop VAB that we call VAB2 is equal to 2 volts. Okay, so the final contribution will be the sum of these two, so that basically we can already say that VAB equal to 7 volts. Now the only thing left to calculate is the equivalent resistance. Okay, for doing so, I will delete this circuit. And I will think about what is the resistance that I see when I from A to B. And for doing so, I have to change my current source with an open circuit and my voltage source with a short circuit. So in this case, I will have something like this. Like this, then open circuit here, this resistor here, then this one here, and then this one here, and open circuit. And I want to see what is the resistance that I see between these 2 points. If I look here, so what we'll find, I will find this R, then no current flows in this branch because it's an open circuit. So current will go this way, then this way, then this way, and then come back to my B point. No current flow in this direction because this is an open circuit. So between A and B, basically I will have 1, 2, 3 kilo. So my R, let's say my Thevenin R is equal to 3 kilo. Okay, so resuming all these calculations, we can say that, I will delete this circuit, we can say that the equivalent circuit, the equivalent Thevenin circuit of this network here, of this circuit here on the left, is equal to a voltage source, which is 7 volt, and a series resistor, which is 3 kilo ohm. And we have resumed our complex circuits on the left with a very much simpler circuit on the right. Please tell me any comments, any question or doubts, or just comment this video in the comment section. Thank you for watching. I hope this will be helpful for your exercise and problem in electronics.